I get your US Shawnee there. All right, we'll get started in about a minute or so. Can you all see my screen?
Yes.
All right, thank you. All right, it's 12 o'clock. We'll get started here. I'm going to go through the determination of equilibrium constant, but only very briefly. This one's due, I guess, tomorrow night. Now, I'm not going to play this video completely. I just want to play a little bit of it. But let's see if I can find the part here where it goes through the table. Can you see the one? Let me turn that volume down a little bit. There we go. See if I can find that final result there. Actually, I'll go back to this one. This is fine. Right, you can see here that we mix these things together, and there's a table that you'll specifically use as well. And let's see, let's pull this up out of the lab manual here. As I mentioned last week, the lab you're doing here, it's not quite in the same order as what's in the lab manual. I am working on fixing that, by the way. But the lab you're looking at will be not this one here as after rates of reactions. That one we'll be doing after pH. So the one we're looking at is after the pH lab in the manual here. And you can see this is what I'm talking about with these various volumes that we're using. We're using FeNO3, which is essentially colorless. It's maybe a very slight yellow color, but essentially it's colorless. And the KSCN is colorless as well. But the compound that we're forming which is this here, this FeSCN2+, is a red compound. The equilibrium itself doesn't go all the way to completion, which is kind of the point of what we're doing. So we're keeping a fair amount of the concentration. We're trying to adjust the concentration so we get varying amounts of this red material at the end, which is why you can see that the more SCN minus we add, the darker the solution becomes, because we're getting more product in those cases. So that's the premise behind it. So the bottom line here is that you'll be doing these calculations, which are going to be based on absorbances that you'll pick up out of the results. And those absorbances were found using a spectrometer. And again, you can watch the video to see exactly how those were obtained. And the absorbance readings, again, are going to be in the results. And I'll pull up another instance of my courses here so I can show you the results. So the results, of course, are in the student data. And the data you're looking at are over here. So you need these absorbance readings. And that's what goes in here. Now, I did get a lab submission the other day where somebody had put in just 447 nanometers. That was the frequency at which these absorbances were taken, but that was incorrect, of course. These are the absorbance readings you're using. Now, from these absorbance readings, we're able to actually calculate the concentration of the FeSCN2+. And you can see we're doing that by taking the absorbance that we get up here and dividing it by this, which happens to be the slope of this line that we get from an absorbance graph, where what we've done here is just taken known concentrations of FeSCN2+, which is red, and then figured out the absorbance of them. And now, if we have a certain absorbance, let's say we had an absorbance of 0.2, I'm hoping you could see that by running it across to the line, we could figure out what the concentration of the FeSCN2+ was. And that's exactly what we're doing here. See, y equals that x. So we can calculate any x value by dividing the y by the slope, which is this. And that's how we're getting all these different x values down here based on certain absorbances. But you didn't have to do that part because we already did it for you. So that's what you're doing. Now, the initial moles of anything is going to, I've got the calculations up here. The volume used and the volume used here are off this table. That was another mistake that I saw some people make here, or one person make, was they were using 10 mils as the volume, but that's just the total volume of solution. These are the volumes you're using in that step, the volume of iron and the volume of SCN. Does anybody have any questions so far? Okay. So once you've done that, then you can do I think the most important step is this subtraction step here. Because I'm just going to go through this briefly. This is probably going to end up causing me to lose my share, but I'll get back in a second. For some reason it's not coming. Give me a second, please. Okay, we're back. For some reason, I'm having a little bit of trouble here. Give me a second. There we go. So if we have a certain amount of Fe3 plus in here, which I'll call X, and we'll have a certain amount of SCN minus, which I'll call Y, and then and that'll be initially, and there won't be any FeSCN2 plus initially. Oops. And then at equilibrium, we'll have X minus a certain amount, Y minus a certain amount, and that amount will match the amount of FeSCN2 plus we get. And we can determine that by looking at the absorbances, which I just showed you. So we get this Z value, and you can see the most important part then is getting these equilibrium concentrations of iron and SCN, and we do that by the subtraction. And you can see that's that step there, Fe3 plus minus the equilibrium moles of this, and SCN minus the equilibrium moles of this. And that will give you the equilibrium moles of Fe3 plus and moles of SCN minus. And after that, we convert that to concentrations by dividing by the total volume and converting it to liters. And then we can get the K value. And the K value is quite simply this. The concentrations all arranged in this equilibrium setup. All right, and that's all there is to it. So this one isn't particularly bad, I don't think. Does anybody have any questions about it though? Okay. Let's go through the next one, which is the pH lab. So the pH and buffers lab is going to, all the stuff here is related to that. It actually goes through a lot of material here. A lot of it goes into detail. But what I've done is I've actually added some stuff into the video here to help you out. Now remember, this is a 2-day lab, so, but it actually, I know with the rates of reactions one, that was complicated. There was a lot of moving parts to that. That was a 2-day lab as well. This one, I don't think it's quite as bad, to be honest. However, now I know this is a long video, and that's kind of why we make it 2 days. It's because there's a long video here that goes along with it. So as you can see, it is an hour. The video is an hour. Now that includes my annotations that I've included in the video as well. So, I know the temptation is not to watch the video. I get that. But the video is important because it gives you some context as to what's going on. And it will enable you to understand better what's going on in the lab. So if I show you here after part A, for example, I go through an explanation of what exactly you just did. And here's an example of that. I'm not going to play the whole thing, just play a little bit for you so you can see what I've done. Oh, that's awful. Why is that? I don't know why that's not very clear. That's disappointing. When I encoded this, it didn't look quite as nasty as that. But I think it'll probably be high enough quality for you to understand what you're doing with it. At least I hope so. Let me look at the other one here. Yeah, it's not very, for some reason it's not very high quality. Well, I hope it comes up better. You know what? It might be just the resolution of my screen, because I've got a different screen resolution due to the fact that I'm using this screen sharing thing here and some other stuff. So I will look into this, but I'm hoping that it will be clearer when you look at it. Has anybody looked at it? Rebecca, did you look at it? You've done this, haven't you?
I have not had a chance to watch the video. Everything I did was from the lab book.
Oh, you did it from the lab book. Okay.
Mm-hmm.
All right. Okay.
No, that's on the agenda for today.
All right. Yeah. It didn't encode up as nice as I had hoped it would, which is really annoying. But anyway, we'll see. It's one of those things you look at it.
Sorry, I just opened the video on my computer and it loaded fine. I'm guessing it's your Wi-Fi or something.
No, it's not the Wi-Fi. I think it's the screen resolution.
Okay. Yeah, it loaded fine for me.
Good. That's fantastic. Thank you, Nathan. I really appreciate you saying that, because now people won't think this is how it's going to look on theirs. But anyway, the point is I've got this stuff here and it's interspersed amongst the video, but I would recommend watching the entire video so you can get an appreciation for what's going on here. And I especially go into all this different terminology of acid, conjugate base, and all of that. And how we can make the buffers up. And there's 2 questions in the lab report that deal with this. So I'm going to pull them up. And for anybody who's here or watching the Zoom, this is going to be incredibly valuable to you, what I'm going to show you here. Now, everything that's in this results report is actually explained in the video in those interspersing parts in between, the parts where I do the explanation. And, you got the part A here. You got the part B. And all of this stuff here, all these calculations are actually explained in the lab. I want to point out, though, this last one here, that this one often people get wrong. I talk about 2 ways of making up buffers. Now, one thing about buffers is that a buffer is a mixture of a weak acid and its conjugate base. And you'll see this when you go through and you look at my explanations here in the videos. And the one way you can make it up is by using just a weak acid and its conjugate base. I go through this here and I show these different methods of doing it. There's a situation where you just have the conjugate base and the acid in there. The conjugate base is the A-, the acid is the AH. And when we add a strong acid or strong base to it, we notice we don't get much of a change in pH because of the presence of these species in the solution. But the other way we can make up a buffer is by adding sodium hydroxide to the acid straight away. I think I show that over here somewhere. And maybe I'll do that in the next page. I think I do, actually. It's coming up. Oh, no, it's on the next page. Yeah, okay. Yeah. So this method here refers to this question here, this question 17. So you might want to mark that down, that this refers to part C, and the calculation is explained in part C, whereas part D, that's where I go into another method of making a buffer. Where we add OH minus straight into the AH solution. Anyway, you'll see the difference between those two, and make sure that you use the correct setup, the equation setup for both of these. I go through, oh, there it is. That's nice now. I go through all of this in the actual lab video, how to get these calculations correct. And you should be okay if you follow what's in the video. Does anybody have any specific questions they want to ask? No, everybody's good with this? Does anybody have anything they want to ask about it? Honestly, I feel like if you watch the video, it should be fine. Remember, it's a 2-day lab, so I can justify a long video on this one. This lab is not due until, oh gosh, what is it today? Tuesday, Thursday, so yeah, it's not due until Thursday of next week, I don't think, or Wednesday of next week. So yeah, you've got plenty of time to get it done. That's why I made it a 2-day lab. All right, so the calculations on this one, they're not particularly complicated. I think you'll be okay with them. All right, does anybody have anything else they want to ask about? I didn't really have anything else I wanted to say about this one. All right, okay, well, I guess we'll leave it there then, if nobody has any questions. And
Excuse me.
yeah, Osha.
With the pH formula,
Yeah.
if they have the same volume, it's just pH equals pKa, right?
That's exactly right, because a log of something over something where it's the same is going to be a log of 1. There it is there. So let's say it's log of 15 over, log of 15 over 15, that'd be log of 1, which is 0. So you're right, the pH will equal a pKa.
Okay. All right.
And if it was, there's another one here, Oshan, it says 2 over, where it's 20 over 2. So that's 20 and that's 2. That'd be log of 10. Log of 10 is 1. So the pKa would be, so pH equals pKa plus 1 in that instance when it's 20 over 2.
All right. Thank you.
All right. Any other questions? All right. If you have any other questions, you can email me, but I think it's pretty self-explanatory if you go through and you watch the entire video. All right. Well, we'll leave it there for today, and I will see you next. Well, actually, I am going to do a Zoom session on Thursday for the class, another one at 10 a.m. Because we didn't get through everything I wanted to get through this morning for the class one. So if you're interested in that, you can visit on Thursday at 10. I'll send out an email and the meeting link and everything for that one. All right. Thank you all. I will see you later.